All right, I think we've had everyone come in that's going to make it in. Thank you everyone for coming. I hope we can all hear me okay. Uh, for those of you who are just joining us, this is a webinar series where we talk about various aspects of capillary scale liquid chromatography. I'm Sam Foster. I'm an application scientist here, and I'm joined today by Dr. Dwight Stoll, who will be talking a little bit more about how to properly select a column using the column selectivity database he has put together. So to start off, in the past couple of talks, we've discussed various aspects of the system in terms of pumping, as well as just various differences with capillary scale. But today, I want to go more specifically into capillary scale columns. So to start off with, I always like to define what capillary scale is, just to make sure everyone is on the same page. We all are kind of aware of what we're talking about. Then a lot of the questions that we get asked, and what I want to start to go over, is analytical scale columns or larger scale columns in general versus capillary scale columns. Then I want to go into a number of non-traditional formats that can often lend their properties well to the capillary scale flow rates, go over some of the existing commercial options, and then I'm going to hand it over to Dr. Stoll, who is going to discuss ways of selecting an alternative column if your specific column isn't available through commercial vendors. So first and foremost, what is capillary scale? Chromatographic scale in general is typically determined based on the inner diameter of the column you're using. 4.6 to 2.1 millimeters in inner diameter, that's typically considered analytical scale, although 2.1 is sort of narrow bore. And capillary scale is really defined as 0.3 millimeters in inner diameter or below. Some places have it as 0.5. It depends on the source. But really what's key about capillary scale columns is the flow rates needed to achieve similar linear velocities. So these three separate flow rates are 1 mil a minute, are 0.2 mils a minute, and are 0.004 mils a minute, or 4 microliters a minute, all give comparable linear velocities or move through the column at the same rate. And so that dramatic change in scale is useful for solvent savings, but it also comes with differences in chromatography that we've been discussing. So the real question that I think we're here to answer today is, are analytical and capillary scale columns the same? And in fact, I want to put a poll out to see what the crowd thinks. So we should be seeing a poll pop up. Do we think analytical scale and capillary scale columns are the same? We'll give it a couple of seconds here for everyone to answer. I'm seeing a lot of no's, a few yeses, but the no's take it 75 to 25. All right. Well, thank you all for answering. The answer is yes, they are the same, but they also aren't. And that's really what we're going to be discussing. So in terms of practical usage, the efficiencies you're going to get out of them, for the most part, capillary scale is going to perform the same as analytical scale. If you get a commercially packed column from a vendor that's been doing it for a while, typically you'll see very similar efficiencies. But how we get to those efficiencies is a little bit different. So I want to pop this up. We often think of the column and sort of the packing in general as this magic separation device, right? If you're an industry chemist, you typically don't care about, your packing methods or the composition of your column, but really there's a lot that goes on in there. And this could be an entire college course, so I'm going to be making a lot of sweeping generalizations today. So that being said, really, there are differences between these columns based on the particles you use, the inner diameters, how you pack them. In this case, we're going to be looking primarily at slurry packed columns, which is a common method of packing both analytical and capillary scale, and really discovering why we see similarities, but also differences between these columns. And a lot of it has to do with something known as wall effects. So when you're packing these columns, you will start to see something that is a wall effect, or a highly dense region, in this case, the red region, of particles directly around the column wall. And these tend to be a very ordered high density bed because all of the other particles are pushing out and can typically make a very dense packing layer. From there, though, we actually see two more distinct regions. We see an intermediate zone. This is several particle diameters thick. And then we see a bulk zone. And the interesting part is that intermediate zone often has a slightly higher packing density than your bulk region. And what that leads to is differences in velocity as you push through the column. So you actually are seeing slightly slower flow on the edges of the column when compared to your central bulk region. That's what we see here, is that we see very low flow and then picking up. And as we hit the bulk central zone, we really start to get to a fairly stable velocity profile. Now, what does that do for our chromatography? Well, it's going to cause some band broadening. As we flow through that column, our center region is going to flow slightly faster than our outer regions. And again, these are, small percentages. We're not talking about very, very considerable amounts, but it is enough to cause loss of efficiency, poorer resolution, and poorer peak shape. So what does all of this matter, right? If we know these exist and we really can't do much to stop them, and there are ways to stop them and different packing methods that can start to mitigate them, why do we see similar performance from both capillary and analytical scale columns? And the answer comes down to the ratio of that intermediate region to its bulk region. So I have a wonderful figure here from a paper by Fabrice Gritty, and what this is a theoretical prediction of column efficiencies based on the various inner diameters. And so what we start to see is that our traditional 4.6 millimeter column or our 2.1 millimeter columns, the bulk region takes a majority of that column space. And so because of that, the wall effects are pretty mitigated. And we see that similarly on our graph over here. Our 2.1 is in red and our 4.6 is in blue. These two are offering high efficiencies and aren't seeing many impacts from that wall region. On the other end, we see the same thing, but inverted on the capillary scale. So we see almost all of the column at 400 micron is that intermediate region with a very small bulk region. And so because of that, the wall effects actually are, because they're the majority of your column, are causing less loss of sample than they, or less loss of efficiency than they otherwise would have. And so we see that that 0.4 millimeter column has comparable predicted efficiency compared to the 4.6 millimeter column. And what we really see is that there's this sweet spot of loss of performance at about 1 millimeter. And again, that's not to say all 1 millimeter columns are bad or all of them suffer from this. There are methods of mitigating these wall effects. But what we do see is that the theoretical prediction is that these 1 millimeter and 800 micron offer very poor performances because the wall region in that intermediate zone have an outsized impact, but don't make up the majority of the column. And so we get very similar efficiencies in two very different ways. And that I want to, touch on is that capillary scale, for all intensive purposes, is the same, but when you start to get very, very deep in, and far deeper than we'll go today, there are significant differences. Additionally, I wanted to touch on heat generation and dissipation. This can really be a factor if you're running, sub 2 or in fact sub 1 micron particles at extremely high pressures. What we start to see is similar to that velocity difference. We'll see a temperature difference caused by the friction of that mobile phase flowing through the particle bed. We tend to see heat generation across the column. And there's really only two ways of dissipating heat once it builds up in that column. The first way is simple. You flow the hot liquid out the end of the column. That one happens pretty quickly. The other way is heat dissipation through the walls of the column. And that one typically will only diffuse through the edges because heat has to dissipate. And so what you see is as you push at these very high pressures, at these very high flow rates, we have extremely high power production. In fact, in some of the examples given, the power was high enough to boil the liquid when it moved from the start to the end of the column. It would go from room temperature to boiling before it ever exited the column. And what that causes is differences in viscosity across the column. where the center region, because the heat isn't properly dissipated, will have lower viscosity and slightly faster flow because it's warmer than that of the edges of the column, which again is going to hurt your efficiency. Because we have less stationary phase, we have less energy or heat production. And so because of that, these temperature effects are felt less when you go down into the capillary scale. Now, a lot of this happens when you're working at 7,000 bar with sub 1 micron particles. So for practical everyday use at not ultra high pressures, these aren't necessarily the most important. But again, when we start to get down into the finer details, they do tend to play a role, and capillary columns start to act a little differently than analytical scale. Additionally, I wanted to go over some of the lesser known but still relevant columns. And in fact, there are a couple of column types here that we're going to talk about that really lend their benefits specifically to capillary for a number of reasons. So we'll get into that. First and foremost, we have monolith columns. So rather than packing a number of smaller particles into the column, we tend to instead make this porous membrane. This can either be a silica backbone or an organic polymer. And the idea of this is that this porous structure can serve similar to a packed column bed in providing a large amount of surface area, while at the same time requiring less packing and can be more easily fabricated. This is just a couple of images of that. And again, we can see that very porous structure, so a very high surface area inside of those monolithic columns. Now, there are a couple of useful benefits to monolith columns. I think first and foremost, they produce a lot of lower back pressures. This can be great if you're trying to flow extremely quickly. This also lends credence to very long columns. As we'll get into, some of these can reach meters in length, which is very different from traditional packed capillaries or packed columns in general. Additionally, there is less mass or reduced mass transfer resistance, which allows for very high speed separations, especially when it comes to large molecules. You don't necessarily have to worry about putting a lot of strain or stress on them. Now, the one downside or the drawback is that typically there is a broader dispersion of these pore sizes. So you'll see slightly lowered efficiency when compared to packed capillaries. That's not to say they can't meet efficiencies. In fact, there are plenty of papers where they do. That's sort of the rule of thumb, though, is traditionally we like to think of these as having slightly lower efficiencies than packed bed capillaries. Our next mode is open tubular columns. And so these really came about alongside that of GC columns or gas chromatography columns, with the idea of having a thin capillary coated with some functional group in order to perform these separations. And in fact, it was actually Milton Lee's group who did some of the initial work with these back in the 70s. The difference really is the inner diameter needed. So with gas chromatography, you have much higher diffusivity because gas can move around a lot more than liquid. Because of that, we really need to go to much smaller inner diameters for these columns to produce comparable efficiencies. In fact, most of what I've seen recommends columns with 20 micron inner diameters or less. And so because of that, you really have to go slow in terms of flow rates to not clog it or overpressure it. They are very high efficiency. We don't necessarily have the same packing concerns when we work with these. We also don't necessarily have to worry about particle size distribution and things like that. We really just have a capillary with a coated layer. They do suffer from drawbacks in terms of loadability. They aren't necessarily the same surface area, and therefore you can't load as much sample onto them as you could with a packed capillary. But they do offer very high efficiencies in a different mode. Another mode that I wanted to talk about is pillar array columns. So these are sort of in the same idea as open tubular, in that if we reduce the amount of heterogeneity in the column bed, we can produce higher efficiency separations. Rather than having a bunch of particles packed in fairly randomly, if we were to make a perfectly homogeneous bed of these pillars and then coated them with a functional group, we'd be able to perform these separations with significant reductions to band broadening. However, it does come with the stipulation that you actually have to make these beds. And so making very large beds or very high pressure beds of all of these different pillars can take considerable amount of time. It often is fairly costly, and they certainly don't necessarily have high enough pressure limits that you'd want to flow through at milliliters per minute. So instead, capillary scale becomes very useful with these columns in terms of hyphenating LC to them. Additionally, these, and I thought this was a really cool graph, is they're able to perform these separations, and much like a packed capillary, the particle size, or in this case, the pillar size and pillar distribution, plays a role and plays an impact very similar to that of particle size, where the smaller you have, or pardon me, the smaller the pillar and the closer together they're packed, the higher efficiencies you tend to see. And so it acts very much like a packed column, but it's made of these homogeneous pillars. And so I thought that was pretty interesting to show. This graph here just shows the differences of a Gen 1 versus Gen 2 column, showing just that, whereas we reduce the pillar diameter and put them closer together, we again see the expected efficiency gains that we would. So this is another method where it requires low, often microliter a minute flow rates, which is great for capillary scale, and offers just a new way of doing chromatography that's fairly promising. So looking at the commercial offerings of capillary columns, there really isn't a phase or a technique you can't find. Really, the only one I found so far is protein A columns, and I'm on the hunt for that. There's some interest there. This was part of a LCGC article that was recently published, going over, to my knowledge, every manufacturer. If you're a manufacturer watching this and you aren't on the list, please let me know. I'd be happy to update that. But this is most of, if not all of, the commercial offerings of capillary columns. And we start to see a couple of key geometries that stand out. Primarily that of the 0.3 millimeter inner diameter or the 0.15 millimeter inner diameter. These are sort of the two most common inner diameters that we find. The standard column lengths, we tend to see anywhere from 5 centimeters to 15 centimeters. We can get really crazy lengths. In fact, if we look at some of these monolith columns, like those offered by GL Sciences, we can get all the way out to 2,000 millimeters, which is pretty ridiculous for a column. But as we can see, there are a number of different phases. C18 is the most common, but we have cation exchange, Hillick, size exclusion, various numbers of them. And what we see, because this list is going to go on for a while, is a lot of sort of the standard column vendors that you'd look at, Waters, Thermo, YMC, Phenomenex, AMT. We also see a lot of distributors. So MacMod, they tend to have their own line, but they also stock a lot of these. So if you're looking for distributors, you'll often find that one distributor can carry many of these capillary brands. We also see that the pressure limits tend to fall in line with that of HPLC columns. They're often either 4 to 600 or 1,000 bar if you're going for UHPLC. Really, the only thing that you can't find with these columns is large particles, and that's for a great reason. Is typically the highest particle size we'll see is about 5. That's not to say you can't pack capillary columns with larger particles. I've packed some with 30 micron and with 10 micron. But really what you see is a significant loss of efficiency. I mean, if you're at a 100 micron inner diameter and you're using 30 micron particles, your bed is only 3 particles across. It tends not to offer incredibly high efficiencies. And so really, basically the sky is the limit with commercial offerings. That being said, we'll get to Dwight in one more slide here. There are certainly phases and columns where we miss. Now, to talk about Axcend a little bit, our system was designed with the intention of connecting to these commercially available columns. So We have a flow rate range of 0.5 to 10 microliters a minute, which is sort of the standard operating range for the most common column inner diameters, the 0.15, the 0.2, and the 0.3 millimeter inner diameters. We're able to accommodate columns all the way up to 15 centimeters in length. So unfortunately, we don't have a cartridge 2 meters long to accommodate some of those monoliths, but we do have, the ability to use the majority of commercially available columns. And we're also able to heat them up to about 80 degrees C, which enables high temperature workflows if you're, doing, high temperature or biopharmaceutical compounds that require temperatures to be that high. Now, the big question is, what if I can't find a column on that list? And I think there's no one better to answer that question than Dwight Stoll.
All right, thanks, Sam. So I think there are a number of different ways one could approach this question of how do I find a suitable column of similar selectivity that meet the requirements that I have for specific dimensions. But the approach that I'm going to talk about here briefly is using the so-called hydrophobic subtraction model of reversed phase selectivity. And the reason this is really powerful here is because we have today a database of selectivity parameters for columns that stands at about 800 columns that's freely available. So that's really a freely available tool that anybody can use sort of in this space. So what I find is that the community is kind of split into two groups. Either there are people who really use this model a lot and know a lot about it, and there's a large population of people who have never heard of it before. So before we get into actually looking at the data, I just wanted to go over some of the basic ideas here so that we're all on the same page. So this hydrophobic subtraction model really started life about 25 years ago. These three gentlemen here were some of the key players early on in the early 2000s, following some what Lloyd Snyder called trolling of retention data. He thought, oh, there really could be a chance here to build a selectivity model that could be used for finding columns of similar selectivity. And so the development phase really persisted through the early 2000s there, and it was a highly collaborative effort involving USP, PQRI, column manufacturers, and some other stakeholders in the industry. Then around 2010, Lloyd and John said, yeah, we're going to retire soon, so we'd like somebody to sort of take over this project. And so at that time, we transitioned the characterization of new columns using this model to my lab here at Gustavus Adolphus College in Minnesota. And we've been doing that for the past 15 years. So as I said, the database currently stands at about 800 columns. Actually, we just have some new data today. We're going to flip over 800 here shortly. And it's growing pretty consistently at about one new column every 2 weeks. So next slide. Yeah, so this is going to be a really brief introduction and discussion of it here, but for people that are interested in knowing more, I'll just point you to two resources here. If you have a short time and you want to know just a little bit more than what I'm saying, then I point people to this LCGC article on the right, published about 10 years ago. It's a 10 or so page read that like I said, gives a little more depth and kind of gives an update on what had been going on with the model at that time. If you want to know a lot more and you have a lot more time to spend, then I refer people to the book chapter indicated on the left, which is just a tremendously rich resource about selectivity, reverse phase selectivity in general, but also specifically this model. So just a little bit about how the characterization works. So the model was initially developed using about 90 different small molecule compounds and 10 type B pure or pure silica C18 columns. And the conditions really since day one pretty much have been acetonitrile and phosphate buffer. So 50-50 mix, 35 degrees. And we do work at both pH 2.8 and 7. since that initial development, the solute set has been reduced to 16. So that's the current characterizations or protocol I'll speak about in just a moment here. But the hydrophobic subtraction model, HSM for short, what it attempts to do is quantify selectivity, where selectivity is defined here as the retention factor of any compound relative to the the retention of ethylbenzene. That's what's in the log term here, as a function of 5 solute column parameter pairs. So, and these are kind of cartoons that try to reflect the chemistry that we try to capture in these terms. So the A to H term is about hydrophobicity. The sigma S term is about solute size, more or less. The beta A and alpha B terms are about hydrogen bonding between the analyte and the stationary phase, and the kappa C term is about electrostatic, or you could say ion exchange interactions between the analyte and some charged functional group or property of the stationary phase. Next slide. So the process, what we actually do to characterize columns that we receive is, first, at pH 2.8, we measure the retention times of 16 probe compounds. We have 3 bases like nortriptyline, amitriptyline, berberine. We have a few carboxylic acids like butyl-benzoic acid. We have a handful of uncharged molecules like toluene, ethylbenzene, and things like that. Those are the probes. And then we switch to pH 7 and we only measure the retention of berberine there. We then take those retention values and we do a multiple linear regression against the solute parameters for the 16 probe compounds that have been established a long time ago. And then finally, we calculate the C parameter at pH 7 using the retention of berberine. And so what we compile in the database are the resulting HSABC parameters that reflect the contributions to retention shown in the cartoons on the previous slide. Next. So when it comes to actually comparing columns in terms of similarities or differences in their selectivities, we use this so-called similarity factor. FS here is the symbol we use. And what it is essentially a distance in 5-dimensional space between the 2 columns. So we can't represent 5 dimensions here. So what this picture shows is 3-dimensional space and calculating the distance between 2 columns in this 3-dimensional space. So the green dot and the green square here represent 2 different columns. And so their H, S, and A parameters define the point in space where that column lives. And the FS value is the square root of the sum of the squares of the differences between each parameter pair. So H2 minus H1, square that, so on and so on for S, A, B, and C. And then we take the square root of the whole thing. So the math is really simple, but conceptually this is what it is. And there are some weighting factors that attempt to, let's say, give equal weight to hydrophobicity and electrostatic interactions, hydrobonding, and things like that. Because if we didn't do that, the hydrophobic term would really dominate things. And from a selectivity point of view, that's not so interesting. And you can see more on the website. I'm going to show you in a moment that you can adjust these weighting factors if you want to do that. The big takeaway from this particular slide is that we have this threshold of 3. Anytime we do a column comparison and we calculate that the FS factor is less than 3, then we declare that for functional, practical purposes, the 2 columns are equivalent. Of course, they will never be exactly equivalent. There are going to be small differences, but from the point of view of practical separations, this is kind of the benchmark, the threshold that we use. Anything less than 3, equivalent. Anything bigger than 3, some degree of difference. Okay, excellent. So you can access the database that I'm referring to here, data for 800 columns, HSABC parameters, two different ways. One is through the USP website. The URL is here. And I think if you can advance one more, Sam. So what is shown in this slide is a comparison of the top column here, the ACE5C18, to everything else in the database, sorted according to the FS factor. So what this table tells us is that out of the other 700 columns, this Develosil ODS UG5 column exhibits the most similar selectivity to this ACE5 C18 column. And you can see a kind of rank ordering there. So there are, looks like six columns that have FS factors less than 3 here, and should exhibit similar selectivities to our target column here. Next slide. So if we look at this in chromatograms, these are the first 3 entries in the table. We just look at these chromatograms, qualitatively, they look very similar. Yes, there's small shifts in where the peaks are, but in terms of actually resolving this mixture, any one of these columns would do fine. Even for the critical pair, there are peaks 3 and 4. Next slide. So the other way to get at the database is through this website that my group maintains, hplccolumns.org. This is just a screenshot of the landing page. And if you go to the next slide, now we bring it to the question we're really trying to address here, which is this scenario at the bottom. I'm running a separation and a kinetic C18. I want to go to a 705 micron column, but the table in Sam's paper tells me that that particular option is not available. So what alternatives are there that will give me the same selectivity, but in a different column dimension? Let's go to the next slide. So I look again at Sam's table and I see, Agilent and some other vendors make 75 micron ID columns. You can pick any of those. And so now I can go to the database and say, I'm looking to replace this kinetic C18. So I select that column in the top there. And then I go to the table and I see, about number 8 or so in the list there with an FS factor of 2.5 is the Zorbax Eclipse plus C18 column. And all of the columns in the table here are sortable, and you can also filter on anything. So I could say, I could have made my life easier here by filtering on Agilent columns if that's what I was looking for in particular. And if I did that, it looks like that would have been the number 1 hit in the list because that's the top Agilent column in the table there. So that's the basic idea. I think HSM is a really powerful tool for making these kind of comparisons, and we've just given you a little demonstration here of how you would actually use it as a tool to answer the question that's relevant here today.
Awesome. Thank you. That was excellent. So we'll wrap up with our conclusions. So first and foremost, our capillary scale columns offer very comparable comparable chromatographic efficiencies when compared to analytical scale. There are a number of different column formats that also can be used at the capillary scale, including monolithic, open tubular, and pillar array. There are considerable commercial offerings for a number of different phases of capillary scale columns in nearly all chemistries and geometries. When a phase is unavailable, feel free to check the column selectivity database, as it'll provide great insights into equivalents or near equivalent columns that will point you on the right track. And that the hydrophobic subtraction model as a whole offers great insights into column selectivity across a wide variety of different chemical properties. For those who have been following the series and want to get a little bit more involved, we have started a LinkedIn group, the Capillary Innovation Forum. Feel free to join, take a look, ask questions. We have a number of experts in the field there who are certainly interested in talking with you and helping to spread the word of capillary scale. Here is our references slide. Finally, I'd like to thank Dr. Dwight Stoll for taking his time today. And I'd like to thank the audience for coming out and listening. And with that, I think we'll open the floor for questions. All right, questions are starting to filter in here. I have a good one. For those who've worked mostly with packed columns, what trade-offs should we expect when trying monolithic or open tubular formats? Yeah, so monolithic formats, traditionally you're going to see reduced back pressures, allowing you to move much faster, operate at higher linear velocities. For open tubular formats, you'll typically see higher efficiencies, but much lower, loadability. And so those are definitely things to be aware of. This is a great question. What effect do non-specific bindings have on capillary columns? Yeah, it's a very great question. So the answer is they have, similar impacts. I haven't necessarily gone about and quantified them. That being said, when you're working with something like a protein, you will see, binding and may have to use passivated columns or may have to do a number of runs to actually coat the column and any surfaces. But after that, you'll see very similar performance again to analytical scale. This is a one for you, I think, Dwight. Can the column selectivity Can the column selectivity database be used for identifying orthogonal columns in 2D LC applications?
Yeah, so as I said, the table, when you use the column comparison tool, the table is sortable. So what we were talking about today is trying to identify columns of similar selectivity to try and identify kind of drop-in replacement. But you can just with the click of a button do the inverse sort on that FS factor and reorganize the table so that the columns at the top of the list are the most different from the target column, at least as measured by this similarity factor. And, that's going to return a lot of possibilities. And so the filtering tools are filtering capability in the table is really effective for sort of narrowing things down to some possibilities. But yeah, it's a good question and another good use of the data.
Awesome. Thank you. We have another one here. What are the compatibility requirements for capillary columns from various manufacturers with the Axcend LC column cartridge? Yeah, there's very few. So I think first and foremost, it has to be less than 15 centimeters. You can have the column poke out the back of the cartridge, absolutely. So if you did want to use that 2-meter long column, go for it. It just may not, look as pretty. That being said, basically all you really need is the proper fittings, in which we have, a number of different fittings that allow for connection with the standard, 1/16, 1/32, and 360 OD formats. And beyond that, purchasing a column that is 15 centimeters or less and hooking it in. It's a very simple cartridge that was designed to work just the same way it works with analytical scale. All right, I see another question here. When scaling a method down to capillary dimensions, what's the most common challenge people run into, and how do you usually overcome it? Yeah, no, that's a great question. I think probably the most common challenge is finding the proper column. From there, it's just math to make sure you have, a comparable flow rate and a comparable gradient. That being said, the other major factor is the limiting of extra column band broadening. And in fact, that's what we'll be covering next time is methods of reducing extra column effects to your efficiency in order to maintain high quality and high efficiency separations. Oh, this is a good one. So Dwight, has the theory of the hydrophobic subtraction model seen any changes since inception?
Yeah, so that's a good question as well. So we, my group, in collaboration with Sarah Rutan from Virginia Commonwealth University, have been looking at this in a few iterations. I would say for the first maybe 20 years, there wasn't a whole lot of 20 years of life of the model. There wasn't a whole lot of changing of anything. But what we did around 5 years ago is basically ask the question, okay, originally the HSM was developed using C18s pretty much. What if we think about refining the model using all of the data that had been acquired since the original development, which included a lot of data on, PFP, phenyl, various polar embedded phases and things like that. So we did that. We referred to that model as HSM2, which involved adding a couple of parameters. And we think that kind of, let's say, tightened up the model in terms of its ability to describe selectivity for things that are not simple alkyl silica phases. More recently, we also talked about an HSM3, which was based on a fairly large, much larger data set than we've been working with historically with just the 16 probe molecules. And we were able to do that by accelerating the retention measurement, and that allowed us to sort of open up the scope to about 90 molecules. And I, we're continuing to work on that, and I think the future will hold some more developments in that space.
Perfect. All right, I think probably we'll have time for one or two more. I see one here. Have I worked with MEMS columns? I have not, actually, and you mentioned taking it offline. Please shoot me an email. I'd be curious to see what you have working on that. That would be something interesting. I see another one here. This one should be for you. How can vendors get new columns added to the column selectivity database?
Yeah, good question. Just shoot me an email. I can typically historically the column dimensions we've used for the characterization have been 150 millimeter length and 4.6 millimeter diameter, but some of the newer columns typically are made in those dimensions, so we can really work with anything. That's just been the conventional dimensions. But go ahead and shoot me an email, and we can tell you a little bit more about our timeline and things like that. And we always kick the data back to vendors before we publish it to make sure everything, there's no unexpected surprises there. But yeah, just get in touch with me and we can work it out.
All right, awesome. All right. Thank you very much, everyone, for attending. Thank you again, Dr. Stoll, for taking the time out of your day to come talk about this. If anyone has any questions, feel free to visit us. And anything else you want to add before we go, Dwight?
Nope. Thanks for having me. It's been fun.
Perfect. Thank you so much again. All right, everyone. Bye.